Okay, so as Amber said, we'll be talking about photochemistry of terrestrial worlds orbiting M dwarfs, and I'm going to do that with the help of TRAPPIST-1 planets, our favorite group of 7 rocky planets, potentially. And the reason I include TRAPPIST-1 here is because for the foreseeable future, it's probably our best hope for comparative exoplanetology around M dwarfs. And there's reasons for that, right? There's 7 of them, and they're also, at least in terms of the flux, could be solar system analogs. So for example, TRAPPIST-1c receives approximately the same volumetric flux as Venus. And while there's not exactly a Mars analog, TRAPPIST-1f will receive about 80% of the flux at Mars. And D and E are presumably receiving fluxes similar to that of Earth or a bit more than Mars. And I will argue there's another type of planet we should be focusing on, which is not included in the TRAPPIST-1 system, and that's Titan-like planets. And okay, that's not supposed to happen over there, but anyway. So TRAPPIST-1h orbits too close to receive the same amount of flux as Titan, but there are some RV planets out there that receive similar flux to Titan. For example, GJ628d, which receives about 4 times the flux of Titan, which it's like putting it around Jupiter, so it's like an exo Ganymede, for example. For reference, a similar a planet receiving the same flux as Titan orbiting TRAPPIST-1 would have orbital period of about 117 days, orbiting at about 0.2 AU. And the reason I want to stress about Titan is because how it relates to the pre-main sequence evolution of M dwarfs. So while Venus analogs, Earth analogs, and Mars analogs are baked for tens to 100 millions of years in the pre-main sequence of these low-mass M dwarfs, Titan-like planets may not. So, for example, here's the tracks for the time evolution of the inner edge of the habitable zone from Lugan Barnes 2015, and for TRAPPIST-1, which is around 0.09 times solar mass, you can see that way back at the beginning, the inner edge of the habitable zone is actually around 0.2 AU. So while the planet would not have evolved like Titan, since at that time it would presumably form more like an Earth-like planet or Venus-like planet, with time, or it would not have lost a lot, potentially, a lot of its atmosphere due to a runaway greenhouse. So it could be something interesting to look at nowadays. And if you go to higher mass M dwarfs, like going out to about 0.3 solar masses, the Titan, the equivalent distance for a Titan-like planet is actually about 1 AU. So there's some interesting stuff that could potentially be done. Okay, so for all the modelers out there, it's not just Venus analogs, Earth analogs, Mars analogs aren't the only game in town. I think Titan analogs could be interesting as well. Okay, but stepping back, so I'm actually supposed to be talking about photochemistry. But what do I mean when I say these potential types of planets, right? What we have here is basically generalized versions of Venus, Mars, and Titan analogs. The way to think about this is we have photochemical models of these actual planets in the solar system, and what we like to do is put them in front around an M dwarf and see how they behave. Now that's very dangerous because a lot of these models are tuned so that they fit Cassini or Venus Express observations. So we like to pull back and generalize it slightly without losing sort of the uniqueness of these particular atmospheres. So what makes a Venus atmosphere a Venus atmosphere? So I argue that a Venus atmosphere has lots of CO2, 10 to 100 bars. It's warm because it's closer in, and it also has all that CO2. And as a result of this higher temperature, it doesn't quite have a hydrological cycle to remove volcanically outgassed gases. So for example, in the Venus atmosphere, in addition to CO2, there's a little bit of water, and of course 3 bars of N2, but also trace amounts of chlorine gases and sulfur gases. And these are trace amounts, ppm amounts, but they are extremely important for the chemical cycles that are happening in the Venus atmosphere. Okay, so we're going to try to see what happens to that chemical cycle when we park that planet around an M dwarf. For Mars, maybe you can think of it as a cooler version of Venus in some ways. And what that means is that there could possibly have been or is still an active hydrological cycle that removes some of these trace gases. So for example, sulfur gases are rained out and forms sediments, minerals in the sediments, as well as chlorine. So what you're left with is still CO2, presumably in this case a thinner atmosphere, 1 bar or less, and also N2 and some water. Titan, of course, is extremely different. It's a highly reducing atmosphere. As a result, you get, in this case, N2 and methane. And it's the photochemical products of these gases that make the Titan hazes, for example. Okay. So what happens when we start putting these atmospheres around M dwarfs? How do they actually change? Well, the reason why they would change, I would argue, are essentially two reasons. One, the spectra is different. So M dwarfs, so in this case, we plot both M dwarfs and K dwarfs, a K dwarf, against the sun. And the difference is that in the NUV, the M dwarfs and K dwarfs are dimmer than the G dwarf. And even in the FUV, it's a little dimmer, although Lyman alpha is very bright, probably on a factor of 10 brighter. And when you get into the EUV, and here we're looking at scaling laws instead of actual observations, because you can't actually observe EUV through the interstellar medium. But the scaling law says you could have similar, even greater fluxes. And these are, actually mentioned, these are all main sequence spectra, right? So we're not looking at pre-main sequences where everything gets much more intense. The other effect is, as has been mentioned during this conference and in previous papers, you could get a lot of atmospheric loss, in particular a lot of oxidation of the atmosphere and the surface and the interior. So that would affect the atmospheric composition. So we combined these two effects in a paper that we published in 2015 for a Mars-like exoplanet. And Mars, because you're essentially dealing with just CO2, water, and nitrogen, has a relatively simple chemical scheme. The most important one is how it regenerates CO2. So CO2 atmospheres are inherently unstable to photolysis by short wavelength radiation. And you need a way to put it back together, otherwise you don't reproduce the observations, right? So the way to do that on Mars is through the Huq cycle. And Huq cycle involves something like an HO2 radical. It reacts with free oxygen in the atmosphere and generates OH, and OH can then oxidize the CO to form CO2 and H. So you can imagine there's a problem, though, if you start removing hydrogen, say due to previous desiccation of the planet. So what we showed is as you decrease the total hydrogen mixing ratio of the atmosphere, you start, not surprisingly, losing that CO2. And I think the key here is not so much that we're losing CO2 and getting an O2, a CO atmosphere, and a CO2 atmosphere, right, the 3-gas atmosphere, but that the trend is not really linear. There's kinks to it. And I won't go into the very specific, I won't give you tons and tons of chemical reactions here, but essentially that's due to different chemical cycles taking over as you start decreasing hydrogen. It's not just this chemical scheme dies and you convert all your CO2 to CO and O2. Instead, you start off chemical cycles that rely on H2O2 photolysis to generate your OH. Later on, you have HO2 reacting with ozone to generate your OH. And eventually, when you get down to really low hydrogen mixing ratios, you start just relying on the brute force way of CO plus O plus a third body going to CO2 plus another third body. Okay. So, yeah. Oh, yeah. Another thing is we generate like 20% O2 in the atmosphere, which is a lot. So what does this planet look like? So this is a reflectance spectrum, and we're going to see plenty of ozone features and plenty of oxygen features, CO2 features, and for a lot of parts, it actually looks similar to what Earth looks like, except for one obvious difference, which is we don't have water. So that's a very powerful discriminant. So if you can see all these photochemical products and no water, you can say that all these oxygen and ozone gases is probably abiotic. Now, switching to Titan, it's definitely more complicated, and because you don't have an oxygen to essentially stop this polymerization process. So on this side, you have methane getting photolyzed and then polymerizing into larger and larger hydrocarbons, eventually forming the benzene loops and going forward into hazes. And on the other side, there you go, you have nitrogen doing similar complicated and frustrating things like forming nitriles, and eventually, again, forming polymers that go into hazes. So again, the chemical cycles are very detailed. But instead, I was just going to show you the results, which is the mixing ratios of a couple of major trace gases. So methane's not, you got methane over there, and you also have some C2 hydrocarbons and HCN. And the thing to note here is that, again, once you put in the more detailed photochemistry that involves these catalytic cycles, such as autocatalysis, which is, autocatalysis, you get different results all over the place, right? So for some of these, like C2H2 and HCN, it doesn't actually change much between the different stellar types. For C2H4, you get a lot more of it for the cooler stars, and for C2H6, it's different for every star. And this is due to a myriad of things, and particularly the specific chemical cycles that actually govern the production and loss of these products, and also the different spectra shape. So really quickly, what does this look like? So this is the emission spectrum, and because it's much cooler, we're looking at very long wavelengths here. Shorter wavelengths is essentially determined by the haze, the geometric albedo. And here, it's actually fairly similar, the only difference being that you get a trade-off in C2H6 and C2H4 abundance. So, what about Venus? So Venus, I think, is particularly important now because of tests. So here is a potential test yield, but cut so that these are just targets that is good for GWST characterization. And the box there is the strike zone. But the Venus zone is here, where there's a lot more. So tests could potentially find a lot of exovenuses, thank you, that could be amenable to GWST characterization in the future. So the time to model these worlds, and by the way, this is for M dwarfs as well, the time to model these worlds and produce potential predictive spectra is now. So, okay, I didn't have time to make like a really nice cartoon of this, but essentially the chemical cycle relies on chlorine and sulfur to combine the recombined CO2 and also generate your sulfuric acid. So chlorine catalysis is very important, potentially very important in Venus atmosphere. So everything's preliminary. Literally started this a week ago, and so essentially what we did was, again, we took a Venus model, parked it in front of an dwarf, saw what had happened. So that's in the yellow and red, and actually the colors backwards compared to the color of the stars, unfortunately. But what we see, again, perhaps to surprise, is that we have less O2 for the M dwarf Venus, and somewhat less ozone as well. But as I said, the chlorine and sulfur species is very important. So what happens if you start decreasing that? So just playing a game, decrease it by 1,000. You actually get only get about order of magnitude increase in the column abundance. So that's it. That's interesting. So that's probably due to there's still comparatively plenty of hydrogen in this atmosphere. So as we go forward, we're going to start pulling the hydrogen out and see what happens to this atmosphere. And another thing to notice is that as we're doing that, not only we might get more oxygen in this atmosphere, but we'll also be losing sulfuric acid. So that's something potentially interesting for M dwarf Venuses, is that if they're if they don't have much hydrogen, they might actually be clear, which presumably will be amenable to atmospheric characterization. So preliminary. Yeah. Okay. So takeaways. Photochemistry is complex. It's not just the most abundant gases that are important, because there's these annoying little trace gases, trace catalytic compounds that really control the abundance of these more abundant gases. But yeah, so also another thing is that I think it'll be interesting to start looking at Titan-like exoplanets around M dwarfs. From anyway, I mean, I think it's just interesting planetary science to see how these things evolve under a different star, and also because they could have been habitable in the past, though not anymore. Well, who knows? And also because of tests, it's already up there. The first data drop, I think, is in like a week or something, and it's potentially capable of finding a lot of exovenuses. And so within potentially 5-6 years, we could be on the way to actually characterizing this. So it'd be great to have a lot of predictive atmospheric models to compare those observations with those. So thank you very much.
We have time for about one question.
Nick, I guess.
How do you propose to actually characterize? How do you propose to characterize the Titan-like planets orbiting M dwarfs?
Yeah. So are you speaking to the fact that they'll take essentially 100 days plus to orbit, or
That and the fact that they're unlikely to transit.
yeah, so it's going to take. So I don't pretend that it'll be a JWST that's doing this. Certainly, it could be future telescopes like Blue Boar, HabEx, what have you. If they orbit sufficiently far away, so early enough stellar type that you could potentially do direct imaging, although it's going to take like a coronagraph or a star shade or something. Yeah.